Okay, so there was transition matrices in yesterday's video, right? Okay, so a transition matrix Tij represents the probability of moving from state J to state I. Okay, and we're looking at uh, this particular transition matrix. While you're writing that down, let me get the calculator to open because we're going to use it a lot today. So notice that the current state eats at cafeteria today is 100% for each one. Okay, the current state has to be 100% for each, but the transition states don't necessarily have to be. That makes sense? Because some could be moving. Yes, it is snowing. Oh, okay. It is known that 792 out of the 964 employees ate at the cafeteria. How will you use the transition matrix to predict how many employees will eat at the cafeteria tomorrow? What do you think? How will I use the transition matrix then? So the transition matrix is T. So I'm just going to multiply, and I have to left multiply this because 2 by 2 by 2 by 1. Remember when we multiply matrices, the insides have to match. And so we always will do transition matrices this way. 792. Um, I need the don't. What's 964 minus 792? So we do that. Okay. So this is, so I just multiply. If I want 2 days from now, what do you think I would do? Do it again or square my transition matrices? Either one, both works. Because like multiplying over here would be the same as squaring. But every time I do a new multiplication or a new transition, I must multiply it left of everything. That makes sense? So either one of those options of square or multiply another one. If for some reason the transition changed, which we're not really going to be doing, but then you would definitely, you couldn't just square, you'd need to left multiply by that new transition. So the results were this. What does that mean? We now have 690 eating at the cafeteria and 274 not on day 2 or tomorrow. So on a certain Monday, it was recorded that 589 ate at the cafeteria. Use the transition to calculate how many employees will eat at the cafeteria on Friday. So how many transitions are we having till Friday? 4. So we're going to do this on the calculator. First thing I'm going to do is get my nose for the first day. 964 minus 589. And I'm going to enter my 2 by 2 transition matrix. And I'm pretty much all for store this as t. I think I showed you guys that yesterday, right? Store it, don't have, don't re-enter it, don't have to copy and paste all the time. Just store it, use the variable. Second, the button above 9 or control, that's the still button, and then just hit a T and enter. So now T to the fourth times 589, 375. And we've got 450 eating at the cafeteria and 514 not on Friday. Cafeteria is getting less and less popular. They got to get better food, I guess, or cheaper prices, or okay. That kind of makes sense. That was pretty easy, wasn't it? So that's long term. Well, that's predicting with Markov chains. They can be used for all kinds of things. I have a video on AI using them. Now we're going to talk about long-term probabilities and steady state vectors. It's a little interesting. If you really forget this, they won't like your work, but you could do, if I want the long-term probability and I know the transition matrix, I could just use my calculator to do it to the, 10,000th power or 1,000th power or whatever. So here I've got this, and I'll show it to you. So we got that 450 at the cafeteria. What would happen if we continued this? And I'm going to do it with the steady state vector, and then we're going to go back and do t to the 1,000 times that matrix. That makes sense? And show that it's going to be basically the same thing. So, but there will be points awarded if there's a problem like this for showing it this way. And the steady state vector of a square transition matrix T is the solution to the matrix Q that satisfies the equation TQ equals Q, meaning your transition matrix is no longer changing it, essentially. That makes sense? I think the first time we do transition matrices, we did one where the schools were changing and 5% went from one to the other and 10% went from the other to one. And when the one is double the population, 10% of 400 or 200 is 20, and 5% of 400 is also 20. So you get 20 going each way. And essentially the school's populations don't change. So how to actually do this in the way that they really want it showed. So show that the steady state vector for this system is this. Well, what that involves doing is taking the transition matrix, multiplying by the steady state vector, and it should equal the steady state vector. And having t entered on my calculator is really nice right now. Is it 385.6? and 570.4. And we get exactly the same thing. That is the exact steady state vector. If I did it to the 1,000, let's see what t to the 1,000 times the one I had above would be. I can get a pretty darn good approximation, but it might not be exact. Oh, I got exact. So if all else fails, you can do that. You probably won't get all the work points. But hey, you're getting the correct answer. You're demonstrating some knowledge. That makes sense. For the assignment now, let's try to do it the right way and get practice doing it the correct way. But so in example 1, the solution used the reduced row echelon form of the matrix to solve the equation system. In the instructions, you can find how to access this feature on your calculator. So I don't know why they were showing it, but okay, this is how you actually calculate it. I'm not sure when they gave me the steady state vector why they didn't do that. But the calculating it is this. I know in general that it's going to be this times yn, y equals yn. That makes sense? So we're going to separate our matrix, effectively do the matrix multiplication and separate it into 2 lines. I will then subtract n from both sides of this one and subtract y from both sides of this one to make it 0. So I've got negative 0.15y plus 0.1n equals 0. And 0.15y minus 0.1n equals 0. Don't try solving this as a linear system. You'll get 0 equals 0. We also know that y plus n equals 964. So we're going to make a matrix out of the 3 things here. Y plus n, that's the total amount. Y being those that go to the cafeteria, n being those that don't. So I've made a matrix. My first line is going to be that. My second, and it probably doesn't matter that much, but go in a semi-logical order. And what we're going to do is what's called reduced row echelon form. So let's take that matrix, let's enter it into our calculator. And none of you guys took pre-calc with me, so you don't know this. Reduced row echelon form on your calculator. Mm-hmm. It's one way to solve systems. He might have had you do it that way. I think it's harder for me to remember. I'm gonna store this one as R instead of T. I'll do this before Izzy leaves quick. Matrix and vector, reduced row echelon form. You could enter the matrix there. So it gives you what the steady state vector was. I don't think this was show. I think what I did was show. But this would be find the steady state vector.
Thank you.
Mm-hmm. That makes sense. You did this in algebra too, as that's one way to solve matrices. This one works particularly well for this. The other methods don't work as well for this because of how the three equations are working. So what does this mean? Ultimately, this means we had essentially our combination matrix, which was 0. What was the variable? Y, n. This is 1y plus 0n equals that. So y is 385.6. 0y plus 1n equals. Does that make sense? And this one, that was what we get when we combine them. 0 plus 0 equals 0. Well, yeah. So you can't just do the standard linear combination. It won't work. Oh, the steady state vector is nobody goes anywhere. Wait, that doesn't make sense. So I think we have one more example. Long-term probabilities are again essentially a steady state vector. Okay. So the steady state vector you found in the example above gave you an estimate of how many employees would eat at the cafeteria if the probabilities within the transition matrix held true over time. You saw you will arrive at this end value independent of the values of your initial state matrix. Okay. Does not really matter what your initial state matrix is because we can get the steady state vector without having an initial state matrix. It's just as a y and an n. Okay. If I went back to this example here, t to the 1000, as long as I keep my numbers the same. As long as I keep the same number of total employees, I still get the same steady state vector. That makes sense? Because ultimately it's transitioning there and then it just stays there. So they're essentially showing if you did this, it would happen. You'd be trending towards it with each one of these. So there are many changes that could occur within a system that could alter the trends of numbers. For example, more people may eat at the cafeteria in winter when they want a hot meal than in the summer when they want to maybe eat outside. Be sure to keep this in mind when working on problems, since exam questions could ask you to reflect on the limitations of the system. They might say, what's the steady state vector? But then what are some limitations of this? Well, yeah, or we hired more employees, or some got laid off, or the rate of transition changed because we had to raise the prices, or we lowered the prices and have discount days and coupons and people come. So in the transition matrix for the game Surya is developing, it's our last one, we have the sunny, rainy. Okay. And again, they keep screwing this up, but it should say rainy over here. Yeah. So whatever's gone on with the formatting. It says find the long-term probabilities of a day being sunny in Surya's game. So 0.75, 0.45, 0.25, 0.55. And I'm going to use S and R has to equal S and R. So when I subtract them over, I get the following equations. And I don't, S plus R. What our total number equation? I don't know. I can't remember. Like S plus R equals 1? 1, 1, 1. Okay. Yeah, S plus R equals 1. The sunny probability plus the Rady probability long term equals 1. So I'm going to end up with this matrix. Let's go ahead and stick that into our calculator. I'm going to erase my equations so that they're not in the way. So I guess the S plus R equals 1 is a trick you can use if there's no amount. Because we're doing probabilities with this. So they're totaling to 100%. Total to 100%. Oops, I want to store this because I can as all. Now I'll go to matrix and vector, reduced row echelon form, R. So the probability of sunny is 64.2%. Probability of rainy is 35.7. Yay, yay, yay. That's it.